Okay, hopefully you made it through that last video alright. I do apologize for the length of that one, but unfortunately there just didn't seem to be a natural place to make a cut. My goal is to keep most of these videos under 20 minutes, but of course, sometimes a discussion can take longer than anticipated. But if you made it through the last video, then that means you've already made it through what will likely end up being one of the longer videos for this course. So, with that behind us, let's move on ahead. In the previous video, we discussed wind loads from a strength design perspective. In this video, we will discuss wind loads from a serviceability perspective. To start, let's consider two common materials found on the facade of a building: a glass curtain wall and a brick veneer. Both of these materials are relatively brittle. We will discuss that term in more detail later, but for now, you can imagine how neither of these materials will be able to bend much before cracking. And so, we need to design a structural system to provide the total wall assembly with enough stiffness so that the architectural materials will not crack. In the case of a tall, multi-story curtain wall, one common strategy you will see is a space frame like this one here. And you can see it looks somewhat like a truss, only lying vertical. However, if the architect does not want to see these metal pieces, we can also use vertical glass fins, as shown in this picture. Both systems are used to provide bracing against wind pressure. When using brick, we are clearly trying to achieve very different goals architecturally, and so we need a suitable structural system to match. Unlike glass, brick is a porous material, and so there is greater risk of moisture entering the building. Hence, the architect will need to include a cavity behind the brick to allow any excess moisture that may get behind the brick to evaporate. Beyond this cavity, there is also a weather barrier, insulation, and possibly other architectural envelope layers. And behind all of this, we have our stud wall. And this stud wall is what we hang our gypsum board or other interior finishes on, and it is also what provides the additional stiffness we need to support the brick laterally. In order to transfer the lateral loads from the brick to the stud wall, we need these clips, shown here. This, of course, requires a great deal of careful work, as the attachments are puncturing through the architectural barriers, creating potential pathways for moisture and heat transfer. But that's a topic for another course. For this course, we need to understand that these clips are here to transfer lateral loads to the metal stud wall. For transferring gravity loads, we will have a relieving angle somewhere else along the wall. Note that the stud wall could also be swapped out for a CMU backup wall for added stiffness and durability, but at the cost of more labor, materials, and increased weight. The next key point to highlight with wind loads for architectural components and cladding is that, just like with strength design, we have different pressures for different faces of the building. In the case of components and cladding, we need to pay particularly close attention to corners of buildings. We refer to these corners as end zones, while the rest of the wall or roof is referred to as an interior zone. And you can see here from this chart I pulled out of ASCE 7 that we have wind loads defined for each of these zones. And just to be clear with what this chart is telling us, here at the top we have our velocity in miles per hour, so in this case 110 miles per hour of wind speed. Here we have the height of the building. In this case we have a total height of 80 feet. Next we have the roof form, either flat roof, gable or mansard, hip roof or monoslope roof. Next we have this load case column, and all that this is here for is to separate the negative pressures or the suction from the positive pressures. We have load case 1 negative pressure, load case 2 positive pressure. And you can see here that with our flat roof, there are no positive pressure values, or load case 2 values, for any of the zones located on the roof, which are Zone 1, Zone 2, and Zone 3. And I'll actually try to color those in because I know that the text is going to be hard to read on the screen. And so again, each of these areas on the roof has an NA for load case 2, or positive pressure. This is because a flat roof will never experience positive pressure. Wind doesn't typically drop down out of the sky, so we only have suction on the roof. Now if we look at the interior zone for the wall, which would be Zone 4, we see that we have a design components and cladding wind pressure of about 34 pounds per square foot. For Zone 5, on the other hand, the corner of the wall, this area has a negative pressure of 63 pounds per square foot. Similarly, the roof interior zone has an uplift pressure of 50.2 pounds per square foot, whereas the end zones 2 and 3 have loads of 78.8 pounds per square foot and 107.5 pounds per square foot. So in summary, end zones will have much higher wind pressure than interior zones. Now, what if our building isn't perfectly square or rectangular? The code likes to make a whole lot of simplifications, and honestly this is a good thing, because if the code tried to account for every single possible thing that an architect could imagine, I don't think there are enough trees on the earth for that amount of paper. So we have to simplify, and we have to come up with boundaries for our simplifications. So in this case, for end zones, the magical number for when something becomes an end zone is when the angle is less than 135 degrees. Anything greater than this will still be considered as an interior zone. So in the case of this building, our end zones will be here, here, here. This is greater than 135, so this will still be an interior zone. This, on the other hand, is less than 135, so that is another end zone. This is an end zone. This angle here is less than 135, but note that we've drawn it on the outside of the building. If we were to draw the angle on the interior, that angle would be 245 degrees. That is obviously much greater than 135, and so that is not an end zone. However, this last angle here, the standard 90-degree corner, this is an end zone. Finally, let's talk about drift. As mentioned previously, buildings move under lateral loading. Sometimes they can move quite a lot, depending on the magnitude of the load applied and the structural system's flexibility. We need to make sure that the building doesn't move beyond a certain level so that occupants feel safe and so that brittle architectural components like brick do not crack. For that, we have a range of total displacement limits for wind loading. If occupant comfort is our only goal, we would set a drift limit of L over 400, where L is the height of the building. If we keep the total displacement below this limit, research suggests that the average occupant will not be disturbed or notice that they are moving. For durability of the facade, we need to control the limit a bit more, reducing it to L over 600 or greater depending on the engineer's judgment. So let's take this building as an example. Suppose this building is 42 feet tall. What drift should we limit our structural system to if we have a brick facade? For that, we simply take 42 feet, convert to inches, and divide by 600. And that will give us our maximum total displacement. And so for this building, we have a limit of 0.84 inches in any direction. Lastly, let's look at an example from the ARE. This question states, for a building designed for downtown Newark, New Jersey, what is the wind exposure category according to the International Building Code? Wind exposure category is a classification that relates to our parameter of surrounding buildings and obstructions. And in the back of ASCE 7, we have these photographs defining exactly what the different exposure categories are. These first three photographs define exposure B. Exposure B is used for suburban and urban areas, with buildings closely packed together of small, moderate, or larger heights, as seen in this last photograph. And so exposure B actually covers the majority of conditions. So a typical building will have a wind exposure category of B. But let's take a look at the other exposure categories. Next we have exposure C, which is for flat, open grassland or open terrain with scattered obstructions. The last photograph we have here is exposure D, which would be a building at the shoreline. So now let's return to our question. Our options here are exposures B, C, D, and E. Obviously, E can be eliminated right off the bat because it is not an exposure category defined in the IBC, leaving us with B, C, and D. Given that this is a typical building located in an urban environment, C and D do not apply, and we are left with B, the typical exposure category. And so that concludes our discussion on wind loads. In the next video, we'll be jumping into earthquake or seismic loads.